Hi dear students, from the chapter Chemical Kinetics. In this video, I am going to discuss about rate law, what is the order of reaction and units of the rate constants. Units of the rate constant. Students, I told you in the earlier class, the total chapter Chemical Kinetics will deals with the two topics mainly. One is effect of concentration on rate of the reaction, other one is a temperature effect on the rate of the reaction. So almost 60 to 70% of the chapter deals with the concentration effect on rate of the reaction. 20% it is with the temperature effect on the rate of the reaction. Okay, general topics 10% it is general topic it is present. What is the rate of the reaction, different types of rate, what is order, and what is the molecularity. These topics are generally we will discuss. In this video we will start our discussion with the effect of concentration on rate of the reaction. Effect of concentration on rate of reaction. Rate of reaction. Students, entire chapter of chemical kinetics will talks about mainly two topics. One is concentration effect on rate of the reaction, other one is temperature effect on rate of reaction. So from this part, effect of concentration on rate of the reaction, in this video we will discuss about rate law, order of the reaction and units for the rate constant. The rate of reaction can be determined by using law of mass action. Which says rate of chemical reaction is directly proportional to product means this is a multiplication, product of active masses of reactants, raised to the power of their stoichiometric coefficients. Students, the rate of the reaction can be determined by using law of mass action. What is law of mass action? Which says rate of chemical reaction is directly proportional to product, this indicates multiplication, product of active masses. Active masses is nothing but concentration in molarities, moles per liter. Active masses of reactants raised to the power of their stoichiometric coefficients. For example, let us take a hypothetical reaction. AA plus BB gives rise to CC plus DD. Then students, rate of the reaction we can write it as rate is directly proportional to active mass of A raised to the power of its stoichiometric coefficient is small a, and the product is B, active mass of B, that is included in the square bracket indicates active mass. Active mass is nothing but concentration in molarity. So B power B we can write. Students, this is rate is directly proportional to The product of active masses of the reactants raised to the power of their stoichiometric coefficients. For example, students, we will take one equation. Decomposition of ammonia, 2NH3 will give us N2 plus 3H2 decomposition. In presence of the PT catalyst, decomposition will take place. Students, by using the rate law expression, by using the law of mass action, we can write rate is directly proportional to active mass, that is active mass of NH3 to the power of its stoichiometric quotient is 2, right. So, students, introduce a proportionality constant, some constant K1, NH3 to the power 2 we can write. Students, if you take this equation in another form like NH3 gives rise to half N2 plus 3 by 2 H2, let us take. Same reaction we are taking now. Then rate we can write now it as R is equal to some K2 multiplied by NH3 power 1. For the same reaction, rate expression cannot be different. This is a decomposition of ammonia, this is also decomposition of ammonia. When we are changing the coefficients, then the rate expression is changing. So, for the same reaction, rate cannot be different. Rate expression or the rate cannot be different. This problem can be solved by using another law which is called as a rate law. Let us discuss about the rate law now. Students, in rate law, the rate is expressed in concentration terms, which influences the rate. For example, we will take a same hypothetical reaction. AA plus BB gives rise to CC plus DD. Students, then rate expression we can write rate is equal to some constant K multiplied by A power alpha B power beta. We can write. Students, here alpha comma beta may or may not be same as A comma B. Alpha comma beta, that is powers of the concentration terms in the rate law expression, that is alpha comma beta may or may not be same as A comma B. Some cases it is same. The reactions can be classified into two types generally, that is elementary reaction, non-elementary reactions. Elementary reactions means which occurs in a single step. Those reactions are called as elementary reactions. Non-elementary reaction means which occurs in more than one step. For the elementary reaction, what are the powers in the concentration terms in the rate law expression? It is same as a stoichiometric coefficients in the given equation, right? So, some cases it is alpha comma beta is same as A comma B. In some cases, in some of the reactions which is not elementary reaction, which is a complex reactions, in that case alpha beta is not same as A comma B, right? So, here order of the reaction we should learn. Order of the reaction, which is defined as the sum of powers of concentration terms, the sum of powers of concentration terms in rate law expression is known as order of the reaction. Order of the reaction. Students, order we can measure by using experiment only. With the experiment only we can measure the order. By seeing any chemical reaction, if it is some equation is given, we cannot predict the order. Order can be determined only by experiment. Only by experiment. So no need to predict that given equation is, it is a first order, zero order, or it is a second order, it is a fractional order, because order can be determined only by the experiment, unless until they have mentioned it as a elementary reaction. In the elementary reaction, we can easily find out what is order of the reaction. That is the sum of the coefficients which is given in the reaction itself. We can call it as a order of the reaction. But for the most of the reactions, we cannot predict the order of the reaction unless until they have given some clue, right? So order cannot be determined directly. Order can be determined only by the experiment. So in this reaction, friends, in this rate law expression, in above rate law, order with respect to A is alpha, and with respect to B is beta. And students, overall order of the reaction is alpha plus beta. Alpha plus beta is overall order of the reaction. In the above rate law expression, order with respect to A is alpha, order with respect to B is beta. Overall order of the reaction means sum of the powers of concentration terms in the rate law expression, that is known as order of the reaction. A plus, this is alpha plus beta, that is called as the overall order of the reaction. Students, now we will take some examples for the different order of reactions. Students, some common examples of reactions with different orders. Let us take first is zero order reaction. Zero order reaction. 2NH3 decomposition of ammonia will give N2 gas plus 3H2 gas. Students, for this reaction, rate law expression R is equal to K into NH3, concentration of NH3 power 0. That means rate is independent of concentration of the reactants. It won't depend on the concentration of the reactants. Generally, students, we have discussed in the earlier classes that rate will decreases as the concentration of the reactant is decreasing. Rate will decreases with the time. Concentration we have taken on the y-axis. So for the reactant, with the time, concentration of the reactant will decreases, rate will decreases. In the factors affecting rate of the reaction, we have discussed that, right? As the concentration of reactant decreases, rate will decreases. But here, if it is a zero order reaction, it is experimentally only determined that this reaction is zero order. So why it is called as zero order? Rate is independent of concentration of ammonia. So with the time, what happens? Concentration of the ammonia decreases, but even though that has no effect on the rate of the reaction. Rate of the reaction is independent of the initial concentration or the concentration of the reactants. Then that is called as a zero order reaction. Similarly, H2 plus Cl2, which gives 2HCl, In this also, even though there is a two molecules are involved, but order of the reaction which is measured by using experiment only, that is K into H2 power 0 Cl2 power 0. It is experimentally determined that the rate of the reaction, this is combination of H2 and Cl2 to give HCl, it is independent of concentration of H2 and Cl2. By seeing the equation, students, we cannot determine that order. That in the questions also they won't ask which is order of, what is the order of the given reaction also they won't ask. And for the first order reaction, decomposition of H2O2 will take, it is a first order, H2O plus half O2. Here students, rate we can write it as K into H2O2 power 1, which is measured from the experiment only. Second order reaction, students, first order means, that is in the rate law expression, the power of concentration is 1. In the second order, esterification reaction, CH3COOH plus C2H5OH, alcohol and carboxylic acid will react to give ester, CH3COO C2H5 plus H2O. Here rate is equal to K multiplied by CH3COOH power 1 and C2H5OH power 1. Here overall order of the reaction is sum of the concentration powers in the rate law expression, 1 plus 1, which is a second order, right? Fractional order also it is there. Order can be a fraction also, fractional order. CH3CHO, which gives CH4 plus CO. In this reaction, rate expression is, rate is equal to K into CH3CHO whole power 3 by 2, which is experimentally determined. It is observed that rate of the reaction is directly proportional to the concentration of the acetaldehyde to the power of 3 by 2. Then the order of the reaction is a fraction, that is a 3 by 2. So students, order can be negative, order can be fractional value, order can be integer value, order can be 0 also. 0 order, we have seen 2 examples. So in this, the rate is independent of concentration of the reactants. Concentration power 0 we are getting in the rate law expression. If it is a first order, R is equal to K into concentration of the reactant power 1. And second order, the overall order of the reaction here, the sum of concentration powers we are getting, which is equal to 2, second order reaction. This is a fractional order reaction, that is 3 by 2 is a power of concentration in the rate law expression. So order is a fraction which is equal to 3 by 2. So students, now let us discuss about the units of rate constant. Students, units of rate constant. Units of rate constant. Students, generally rate constant is expressed with the letter K. Rate constant is generally expressed with the letter K. It is also known as velocity constant, specific reaction rate, all these terms are same, which is known as a rate constant K, and it is also known as velocity constant, specific reaction rate. All these terms are same, indicates the same, right? Let us take hypothetical reaction. AA plus BB gives rise to CC plus DD. Students, let us assume that the rate of the reaction R is equal to rate constant K into a power x and b power y. Okay, that is x comma y may or may not be same as a comma b. Let us assume order of the reaction, overall order of the reaction is n is equal to x plus y. N is equal to x plus y. Overall order of the reaction is x plus y. Then students, we can write this expression rate as R is equal to rate units. We are writing rate units in SI system. We can write it as concentration divided by time. So that concentration units in SI system is mole per liter. Concentration divided by time. So let us substitute the units here. Concentration divided by time. Concentration divided by time is equal to K into, students, here overall order of the reaction is N. So this indicates concentration. This is also indicates concentration. So we can write it as a concentration power N, because overall order of the reaction is N. So this is concentration. Bases are same, powers can be added. So concentration power x plus y is the same as a N we are writing. So we need the units of K, rate constant. K is equal to concentration divided by time. By transferring this term to the opposite side, we will get here it as concentration power minus N. Transferring this total term to this side. So this implies K units will get concentration power 1 minus N time inverse. Students, these are the general units for the rate constant K if the order of the reaction is N. Nth order reaction, these are the units. Now let us take for the zero order, first order and second order reactions. Students, for nth order reaction, units of K is concentration power 1 minus N time inverse. Time inverse is a nth order reaction, units of K rate constant. For zero order reaction, students, n place we can substitute as 0, n is equal to 0. Then units of rate constants, units of K is concentration power 1 minus 0 divided by time or time inverse, which is concentration power 1 time power minus 1. Students, these units are same as a rate units. Rate units are concentration divided by time. So students, from this we can write it as this itself. It is an important question. Sometimes they will ask, right? If the rate constant units are same as rate units. Rate units are concentration divided by time. Then order of the reaction is zero order it is, right? Students, similarly for first order reaction, let us substitute n is equal to 1 in this formula, in this units. K units, rate constant units, concentration power 1 minus 1, n place we are substituting 1 for the first order, time inverse. So that means 1 minus 1 0, concentration power 0, anything to the power 0 is 1. So K units are time inverse. So students, we can also predict the order of the reaction. If it is a first order, the units of rate constant is time inverse. Students, similarly we will do for the second order and third order. Students, for second order reactions, in this units of K expression, let us substitute n is equal to 2 then, right? N is equal to 2. Units of K is concentration power 1 minus n place we are substituting it as 2 because it is order is 2, time inverse. Then units will be concentration power minus 1 time inverse. Concentration power minus 1 time inverse. Similarly, for third order reaction, n is equal to 3. Units of K is concentration power 1 minus 3, n place we are substituting 3 now, time inverse, which is concentration power minus 2 time inverse. Students, maximum order of any reaction is 3 only. Maximum order of any reaction is 3 because simultaneous collisions between more than 3 molecules is impossible. Students, in detail about this statement, maximum order of any reaction in the nature, generally it is 3 only. So the reactions with the order more than 3, it is not possible in the nature generally, because reason is simultaneous collisions between more than 3 molecules at a time, more than 3 molecules cannot collide. So this clearly we will learn in the topic collision theory, right? Thanks for watching.